Delaware Tech, Chemistry 100, Chemistry 110, Unit 3 continued, atomic number and mass number. So atomic number and mass number are numbers that relate to each atom of any element. And the first number, atomic number, which is sometimes abbreviated as AT.NO for number, or simply Z. Z is from the German word Atomzahl, which just means atomic number. Atomic number is just the number of protons. The number of protons is the only thing that determines what element that atom is. Nothing else determines it, not the number of neutrons, not the number of electrons, not its charge, only the number of protons. So if I tell you it has 6 protons, you know it's carbon because the atomic number of carbon is 6, and therefore it has 6 protons. In a neutral atom, that is, the charge is 0, well, the positive charges from the protons must be exactly equal to the negative charges of the electrons. So in a neutral atom, the number of protons will be exactly equal to the number of electrons. The mass number is the other number that's important for each individual atom of any element. It's sometimes abbreviated A. It's also known as the isotope number. So you might have heard people say, oh, what's this isotope, or this isotope of some element might be radioactive. Some are not, some are. Isotope number and mass number really mean the same thing. And mass number is the number of protons plus the number of neutrons. And these are the two heavy particles in the nucleus that really give most of the weight to an atom. So if you just count them up, it gives you a rough idea of how heavy that particular atom is. So each atom of a specific element will have only one number of protons. All carbons have 6 protons. But some carbons have 6 neutrons, some have 7, some have 8, etc. So the total, the mass number, might differ from atom to atom, and therefore the isotope number may differ. The A comes from Atomgewicht, which means atomic weight, which is the old name for the mass number. So we don't use that anymore. We don't use weight, we use mass, and we're talking about the number, not the actual average weight of the atom. We'll get to that in the next module. So, as I stated, the mass number really tells you which isotope something is. So, isotopes have a lot of different definitions. As long as you state 2 things, one that talks about how many protons and one that talks about how heavy the whole thing is, those things together will combine to give you a definition of isotope. So you can define isotopes as having the same atomic number, but a different mass number. Or the same element, but they're different masses, which is really the same thing. Or the same number of protons, which is the atomic number, and different numbers of protons plus neutrons, which is the mass number. Or you could just simply say the same number of protons and different number of neutrons. Or if you want to use the abbreviations, they have the same Z but different A. So there are lots of ways of saying things are isotopes. You should be aware of all of these, though Z and A is not something that we use very frequently in Chem 100 and Chem 110. So when you want to say what the element is, when you actually want to verbalize what element isotope you're talking about, you would put the isotope number or the mass number in the upper left-hand corner of the symbol of the element. So carbon is C, and you would put, if you were talking about a mass number of 12, you would put the 12 in the upper left-hand corner next to the C and call it carbon 12. We don't say anything about the protons because we just said it was carbon, and it's understood by all chemists that carbon means 6 protons. So if we said carbon 14, well, carbon 14 must mean that it's heavier, and therefore it still has 6 protons because it's still carbon, but it has 8 neutrons for a total of 14. Likewise, if somebody said uranium-235, that's 92 protons because that's what uranium is, and 143 neutrons, you'll notice they add up to 235. So, going over these definitions, atoms are essentially particles that have equal number of protons and electrons. So the proton number equals the electron number. And that's essentially any element on the periodic table as a single unit. So just reading from the periodic table, you can pick any one of the 118 boxes and write down that symbol, and that would be a single atom of that particular element. Now, ions have a charge, and they could have a negative charge or a positive charge. And therefore, if they have a charge, that means the number of protons with positive charges does not equal the number of electrons with negative charges. If they have extra electrons, they've gained electrons, they have too many negative charges, and therefore they're negatively charged, or they have an extra negative charge. If they've lost electrons, well, then they become positively charged because now the protons outnumber the electrons. In regular chemistry, atoms will only gain or lose electrons. We don't touch the number of protons because that would change the identity of the atom itself, the element itself. And that only happens when we're talking about nuclear chemistry, where we're actually affecting the protons and neutrons in the nucleus. That's why it's called nuclear chemistry. So examples of ions are anything with a charge that's not zero. H plus, H minus, Li plus, that's lithium ion, Na plus, sodium ion, etc., all the way down to uranium plus 3. And you can say these as uranium plus 3, you can say magnesium plus 2, you can say in the first case hydrogen plus. Well, there's only one version of plus, so we just say hydrogen ion, and we'll talk about this a little more when we get to nomenclature in Unit 4. Likewise, magnesium plus 2 is the only common ion of magnesium, so we just call it magnesium ion. Isotopes are atoms, as I said, that have the same number of protons but different number of neutrons. And those can be in the form of plain atoms if the electrons are the same as the protons, or they can be ions if the electrons have been gained or lost. So isotopes can be either atoms or ions, but they are different in mass from their other isotopes of the same element. So examples would be hydrogen 1, 2, and 3. Those are isotopes of hydrogen. Carbon 12, 13, and 14, isotopes of carbon, etc., etc. So let's look at how we write these symbols to show the atomic number and the mass number of these elements. Well, first of all, we write the symbol, and it's 1 or 2 letters for all the elements, and we put the atomic number in the bottom left-hand corner, or we don't bother writing it at all. Because remember, knowing the element tells us what the atomic number is just by looking on the periodic table. The mass number, however, is never found on the periodic table. You won't find it there because every element can have more than one mass number, or more than one isotope. The mass number is the number of protons and neutrons. The atomic number is just the number of protons, and that is what tells you what element it is. So if somebody gave you the atomic number, that's the same thing as telling you the number of protons, but it's also the same thing as telling you what element it is and what symbol it is. So those 4 pieces of information are all really one thing. We usually put the charge of the element in the upper right-hand corner, and if it's 0, most of the time we don't bother writing it. If it's -1, we just write negative. If it's +1, we just write positive. If it's more than one charge of either positive or negative, we have to put the number, and we can either write it, if it was, say, +2, we can write it 2 plus, or we could write it +2. We could even write it ++. All 3 of those are acceptable. When you start getting bigger charges, like +4, +5, we don't write plus, 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 plus. That would be kind of silly, but we would write 4 plus or +4. Either is acceptable. And in the bottom right-hand corner, this corner is reserved for when you're talking about the element being part of a compound and you want to tell the reader how many atoms of that element are in your molecule or in your compound. So each corner has a very specific role in writing, and please don't confuse these corners. Now you'll notice if you just take the mass number and subtract out the atomic number, so the mass number minus the atomic number, well, that's just equal to the number of neutrons. So here's an example. Here's the full symbol. You see there are 3 numbers that are surrounding it in 3 of the corners. And this is a typical symbol. We don't always write all these numbers. Sometimes we'd only write the +3, sometimes we'd only write the 56, depending on the context of how we're using it. But let's ask some questions here. This gives us all the information we need to know about how many protons, neutrons, and electrons are in this particular isotope of Fe. First of all, Fe, we look on the periodic table and we know that Fe is iron. It's actually named for the ancient word for iron. The ancient Romans called it ferrum. This is why we call things that have iron in them ferrous metals. So Fe is iron, and we know the number of protons is the atomic number, 26. We also know the mass number is 56, and that's the protons and neutrons. So taking the difference between the two gives us the number of neutrons, which in this case is 30. 56 minus 26 is 30. We also notice that the charge is +3, and this tells us something. Now, you could use the little formula that's written up at the top, that number of protons minus the number of electrons equals the charge, but I think it's much, much easier to just use common sense. Telling somebody there's a charge of +3, remember, electrons have a negative charge, and they're the only things that change in normal chemistry. If you have a +3 charge, that means you're missing 3 electrons. You used to have the same number of electrons as protons, 26, but now you're missing 3, so you're down to 23 electrons. So you'll notice these 3 numbers will tell you everything. You don't even need the symbol, because once you know that the proton number is 26, you know it's iron. There is no other choice. So let's look at some examples. Here's another one. The symbol is F. There's 19 in one corner, 9 in the other corner. What's the atomic number? Well, remember the atomic number is the bottom left, so that would be 9. And the mass number, that's the protons and neutrons, that's in the upper left-hand corner, that's 19. So 9 and 19 are your 2 numbers. What's the number of protons? Well, the atomic number is the number of protons, 9. What's the number of neutrons? Well, the neutrons are just the difference of those 2 numbers. 19 minus 9 is 10. And the charge, you'll notice there's no charge written. If there's no charge written, you assume it's 0. The number of electrons, well, if your charge is 0, you automatically know that the positive charges have balanced out all the negative charges, and therefore the number of protons must equal the number of electrons. So that would give us, and I'll write in these numbers. Oops, let's try that again. Put that back. And we'll write these numbers in here. So we know that in this particular example, the atomic number is 8. The mass, I'm sorry, 8. It is 9, excuse me. Atomic number is 9. The mass number is 19. That tells us the number of protons is 9. The number of neutrons is the difference, so that's 10. The charge is 0, and that tells us the number of electrons must be the same as the number of protons. Here's another example. Br is 80 in the upper left-hand corner and a negative sign in the upper right-hand corner. So what do you know? Well, Br is the symbol for bromine. You'll find it on the periodic table, and you'll find it at number 35. So I'll just put that 35 in there. And the charge says negative, so you know it really means -1. Well, we know the atomic number is 35. And that tells us that the number of protons is also 35. Remember, this number, this name, this amount, and this amount are all exactly the same piece of information. The mass number is 80. That's in the upper left-hand corner. The number of neutrons is the difference between 80 and 35, which in this particular isotope of bromine is 45 neutrons. Some bromines have a different number. The charge on this bromine says -1, and therefore we know there's an extra electron. There's an extra negative charge. There must be an extra electron. We started with 35, the same number as the number of protons, but we have an extra one. So this tells us we now have 36 electrons in this case. And this is how we do it. And it all depends on what information you're given each time. So I'm going to clear this, and we'll move on to the next example. So here's an example. You're not told what element it is. You're told that the atomic number is 34. Okay, you can look that up. And the mass number is 78. You can never look that up. So atomic number of 34, well, that tells us there are 34 protons. That tells us the atomic number is 34. So we must be talking about selenium, Se. Selenium was named after Selena, the goddess of the moon, also known as Selene, the goddess of the moon. So we know this number is 34. We can write that right in there. We are told the mass number is 78. Okay, well that makes it easy. So we now know the number of protons, and we know the number of protons plus neutrons. That'll allow us to calculate the neutrons. So what are we asked for? Well, we're asked for everything. The number of protons is 34. That was easy. The number of neutrons is the difference between 78 and 34, so that would be 44 neutrons. The charge, well, nobody set a charge, so you assume it's 0, and therefore you know the number of protons is the same as the number of electrons. And the complete symbol would be right here. And you don't need to put the charge there since it's 0. You could simply put this symbol here to represent your isotope. And in this case, since the charge is 0, this isotope happens to be an atom. Here's another example. A neutral atom has 91 protons. That's our Z number. That's our atomic number. And 140 neutrons. Oh, well then we can add those up and get our atomic number. So what are we asked for? Well, the same as always. We're asked for protons, neutrons, and electrons, the charge, and the full symbol. Well, if we know it's 91 protons, we now look it up on our periodic table, and we see 91 is way down at the bottom. 91 is protactinium. Protactinium has a symbol Pa. Protactinium. So we know the atomic number is 91 on all protactinium, but we know this particular one has 140 neutrons. When we add those two numbers together, we get 231 as our total protons and neutrons. 231. So now we know this is 91. We're told this is 140. We're not told a charge specifically, but it says right here it's neutral. So we know that's 0. So the charge is 0. And whenever the charge is 0, the protons and electrons must be the same. So that's 91. And the complete symbol is here. And you don't really need to put the 0 in, but you can. Let's look at one more example. A neutral element, okay, you know the number of protons and electrons are the same, has 78 electrons. That tells you something. There must be 78 protons too. Otherwise, it would not be neutral. And now you know all three things. Well, look up on your periodic table, what is 78? And you can see that 78 is a very expensive metal, platinum. The symbol for platinum is PT. Those of you who know Spanish know that plata, or a word close to that, means silver, and that's because platinum was actually named after silver because it looked like silver. It's actually much more expensive. So we know it has 78 protons too because it's neutral, therefore its atomic number is 78. We're told how many neutrons there are, so 78 plus 117 neutrons gives us a total of 195. That's our mass number. And we told it's neutral. So we have everything here What are we asked for? Well, the atomic number, that's right there. That's our Z. Our mass number is right there. Our number of protons is the same thing as the atomic number, and the complete symbol is right here. So let's look at a typical problem for an exam where you're given a table and you have to fill in the boxes. And you'll notice in each line, in each row of this, is a different problem, and you're given different pieces of information each time. So you have to be careful about calculating. It's done slightly differently each time. But remember, you have lots of clues. You know that the symbol, the atomic number, and the number of protons are really all one piece of information. In fact, this says magnesium, Mg. Well, that's the same thing as telling you atomic number of 12 or 12 protons, so you can already fill in 12 here and 12 here. That's easy. You're told the mass number is 25. So that's the number of protons and neutrons, so you must need 13 neutrons. You're told, and then the mass number you can just fill in directly here, 25. And then you're told the charge is 0, so the number of protons equals the number of neutrons. That's 12. And if it's neutral, it's an atom. We'll just put an A there. So that's that row. And I'm going to delete that and show you that it's actually already on the slide, filled out. The next example, you're given the numbers, you're not even given the symbol. Immediately, the first thing you should look at is that number, the atomic number. And that tells you we're talking about number 13, which is aluminum. So we know the atomic number is 13. We know the proton number is 13. We know the mass number is 27, also known as the isotope number. Well, if the total proton and neutrons are 27 and the protons are 13, we must have 14 neutrons. We are now told it's a positive 3 charge. Well, that tells us immediately it's an ion, not an atom. And positive 3 means we're missing electrons. Well, we started with 13, we lost 3, and this is where students get confused. They see plus 3 and they think, oh, I need to add. No, no, no. Remember, it's electrons which have a negative charge, so you have to wrap your brain around the fact that you're always moving negative things. So it's frequently the opposite of what your first guess is in your head. It takes a long time to get used to that, but do your best. So positive 3 means you're missing negative charges. You're missing electrons. Therefore, we're only down to 10 electrons. So I'll delete this row and fill it in with that. The next one, you're given a different piece of information. And actually, you can practice these on your own. I'm going to take one of the harder ones. Let's take the second to last example. So you're given a mass number, you're given an electron number, and you're given a charge, and nothing else. So this shows you that you really only need 3 specific pieces of information to get everything. Not just any 3, but 3 pieces of information that can allow you to get all the pieces of information. Well, what can you do? Well, the first thing you would look for is the number of protons, and you'll notice there's nothing here that tells you the number of protons. We're talking about this example here. There's nothing that tells you the number of protons, but you do know the number of electrons, and you do know the charge. The charge tells you you have 1 extra electron. Well, 54 is 1 extra. I must have started with 53 protons, and now I know the atomic the atomic number and the proton number. We go to our periodic table, we look for 53, and we realize that's iodine, symbol I, and we can write 53 down here as well. We know the mass number, so we can just fill that in directly. And now the only thing we're missing is whether it's an atom or an ion and how many neutrons. Well, we know it's an ion. It has a negative charge. And we know the total number of protons and neutrons is 131, and the protons are 53 of those, and we subtract that out, and we get that there are 78 neutrons. And so we end up determining this table with a full symbol, I-131, and that we would call this I-131 or iodine-131 with a negative charge. And I'm going to delete these, clear it, and I'll just show you the answers for each row. And you can stop it between, though it might be a little tough, and see if your answers match this table. And with this, we'll stop